Hello, in this video we are going to talk about the Buckingham Pi Theorem and the method of repeating variables. So loosely, the Buckingham Pi Theorem states that if there is a physical meaningful equation involving a certain number of n physical variables, then the original equations can be rewritten in terms of a set of pi equal n minus k dimensionless parameters, which are pi1, pi2 up to pi p, constructed from the original variables. The easiest way to apply the Buckingham Pi Theorem is the method of repeating variables. Let's assume a cylinder of diameter d in a flow with velocity v of a fluid with density ρ and viscosity m. This cylinder is seeing a force F, and this will be our physical equation. So step 1 of the method of repeating variables is listing the parameters. So we have 1, 2, 3, 4, 5 parameters. The second step is to list the primary dimensions in each of the parameters. The units of force are mass, length over time square. The units of viscosity are mass over length time. The units of dimension is length. The units of density is mass over length cube. And the units of velocity are length over time square. The third step is to set the reduction j as the number of primary dimensions. So the primary dimensions repeating themselves here are mass, length, and time. J equals 3. Now we need to calculate k, which is the expected number of p's, as k is n minus j. We already know that n is 5, so k will be 5 minus 3 equal 2. Step 4 is to choose the repeating parameters. This is maybe the most tricky step. Usually, the repeating variables or parameters are the parameters that we don't want to study. In this problem, this will be the diameter, the density, and the velocity. In step 5, we need to construct the k number of pi's and manipulate as necessary. To do this, we'll start with pi1 will equal viscosity times the repeating variables d, r, v on the exponents a, b, and c. Let's look at the units here. Viscosity units are mass over length multiplied by time. Diameter is length to the power of a. Velocity will be length over time to the power of b. And density will be mass over length to the power of 3, and all this to the power of c. So for the mass, we have one mass here and one more here. So for the mass, 0 must be equal to 1 plus c. For the length, we have a length here, 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 and here. So 0 must equal minus 1, because this length is in the denominator, plus a, plus b, minus 3c. And finally, for the time, 0 must equal minus 1 minus b. We have a system of 3 unknowns, a, b, c, and 3 equations, and we can easily solve it and find that c is minus 1, b is minus 1, and a is minus 1. Now our pi 1 can be rewritten as pi 1 equals m over dvr. At this stage, we need to check that this parameter pi 1 is non-dimensionless. So units of viscosity are mass over length multiplied by time. Units of diameter is length, so it will be 1 over L. Velocity is length over time, so inverse will be T over L, and density will be length cube over mass. Mass with mass will cancel out, length, and length with length the cube will cancel out, and time will cancel out with time. So our parameter pi 1 will be dimensionless. We can manipulate pi 1 and define pi 1 prime as 1 over pi 1. And this will give us rho v d over viscosity, also known in fluid mechanics as the Reynolds number. Exactly as we constructed pi 1, we are going to construct pi 2. But now, instead of using mu, we are going to use the force F. So pi 2 will equal F times the 3 repeating parameters d, v, rho, the power of a, b, c. Again, the units of force are mass, length over time square. The units of diameter are length to the power of a. The units of velocity are length over time to the power of b, and the units of density are mass over length cube to the power of c. And we repeat the same process we used before. We will start with the units of mass. So pi2 needs to be a dimensionless number. So working on mass, 0 must equal mass to the power of 1. So 1. There's another mass here, the power of c. So 0 is 1 plus c, or c is minus 1. Now moving to the units of length, we have length here, 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 and here. So 0 must equal 1 plus a plus b minus 3c. And finally, the units of time, 0 must equal 2 on the denominator would be minus 2 minus b. So from here, b equals minus 2, and then replacing here, we have that a is minus 2. Substituting the values of a, b, and c on the definition of pi2, we'll have pi2 equals force d to the minus 2, so I'll put on the denominator d square, v to the power of b, b is minus 2, so velocity square, and density to the minus 1. So, like we did earlier, we need to check the dimensions here to make sure that pi2 is non-dimensional. So force is kilograms meter over second square. The diameter will be 1 over meter square. Velocity square will be second square over meter square, and the density will be meter cubes per kilogram. Kilogram with kilogram will cancel out. Meter square, meter cube will be meter to the power 4, meter square, meter to the power 4, so the meters will cancel out, and the same for the second square. Now, we can manipulate this pi, and we have a diameter square, and we all know that area of a cylinder is given as pi d square over 4. So we can define pi2 as force over 4 pi area velocity square density. Manipulating pi2 even more, we can define pi2 prime as force over half area velocity square density, which is also known in fluid mechanics as CD. So now we started from 5 parameters and we end up with 2 pi's. Which means that we can now describe the problem as using only 2 pi's. And we can say that the drag coefficient is a function of the Reynolds number. And we can plot on one axis the drag coefficient and the other the Reynolds number, and take data and describe our problem.